Hey, what's going on? Today we are going to be looking at percent yield in stoichiometry. So what is percent yield? Well, it's defined as the ratio of actual yield, which will come from actually doing the experiment, to theoretical yield, which is what you'd theoretically calculate should be your amount. And of course expressed as a percent. So you all know the term yield, like the arrow in this chemical reaction symbols. So we're just basically looking at, of all the amounts that should have been created theoretically, how much or what percent actually was created in the lab. Well, you saw it's a ratio of actual yield to theoretical yield, so let's define those terms. Actual yield is the amount of product that is actually produced when a reaction is carried out in an experiment. This would be you working in a laboratory setting, you measuring out a specific amount of reactant, and you measuring or determining the specific amount of product in the laboratory. Whereas theoretical yield would be all paper and pencil. I would tell you you start out with this much and ask you to calculate the amount that should be produced. Theoretically, it's the maximum amount of product that can be produced from a given amount of reactant. And note the term maximum. Obviously, this calculation would be if all conditions were perfect in the lab. This number would be the most you could obtain. When you calculate a ratio of product from reactant given, the amount of product produced, that's really all you can get. So there's no way to go into the lab and end up producing more than what you should be able to get. Now obviously there's ways to produce less. Different laboratory error, human error, anything, any mistakes, any loss of reactant could result in you producing less. But theoretically, you could not produce more than this amount calculated. So we look at our star chart and we see the formula for percent yield. Here it is. And it just says it's a ratio, again, of actual yield over theoretical yield. And of course, you get percentage times 100. Notice theoretical yield on bottom. That's going to be the bigger of the two numbers because, again, it's the maximum amount produced. You may actually produce 100% and match that. Typically, you'll actually produce less. So in this case, you will see consistently the smaller number should be on top. So again, breaking down this formula, actual versus theoretical. Actual is what you did in the lab. Theoretical is what you calculated on paper. So we're looking at our recipe for lead-2 nitrate once again, and we can see the mole ratio here provided by the coefficients. So here's the scenario. You have 265 grams of lead-2 oxide in the laboratory. You have excess nitrogen dioxide and oxygen, so no need to worry that those will limit your reaction. All 265 grams of lead-2 oxide will react. So you conduct the experiment in the laboratory and you measure the amount of product that you produced, and you saw that you found that you had 387.6 grams of lead-2 nitrate produced. So we want to know what your percent yield was. Let's first stop and think about this 387.6 grams. What does this value represent? Our actual yield or our theoretical yield? Well, of course, this is our actual yield. We actually performed the reaction shown in the laboratory, and we actually measured 387.6 grams of product. Now, is that what you would theoretically get if all 265 grams of lead-2 oxide reacted perfectly? Well, to determine that, we're going to have to rely on some stoichiometric calculations. So you've seen this problem before, 265 grams of lead-2 oxide. get rid of grams of lead oxide and convert it to moles. Now that we're in moles of substance A, we could relate it to substance B using the mole ratio. So get rid of moles of lead oxide, lead 2 oxide, and convert it now to our product in moles of lead 2 nitrate. Again, you can see how our units are canceling out nicely. Now we want to cancel out moles of lead 2 nitrate, so we place that on the bottom and convert it to grams of lead 2 nitrate. Using the conversion factors we know, like molar mass, 1 mole of lead 2 oxide is 223.20. The mole ratio is a 2 to 2 mole ratio, and the molar mass of lead 2 nitrate is 331.22 grams. Calculating the math, we've seen this before, 393 grams of lead 2 nitrate theoretically should have been produced had everything in the laboratory worked out perfectly, had all reactant completely undergone this chemical change and produced all lead nitrate that's possible. So let's analyze our values. We started with a amount of 265 grams of lead 2 oxide. Now in the lab, this produced 387.6 grams of lead 2 nitrate. However, on paper, it should have produced a total of 393 grams of lead 2 nitrate. So you can see again how theoretically what we should have obtained gives us the ideal circumstance, and it is more the maximum amount that can be produced, whereas the actual yield accounts for any lab issues and is going to be smaller. To apply this to the formula, we simply divide actual, 387.6, over theoretical of 393 times 100, and you get a percentage of 98.6%, so not a bad yield. What this means is, obviously if we had 100%, we would have had maximum yield. All reactant was efficiently used, effectively used to produce 100% of the desired product. What this means is, in this case, is only 98.6% of what should have been produced was actually produced. So not too bad. Obviously, the lower the percentage would mean we're not getting maximum yield. We're not producing as much as we should. So this is percent yield at a glance. Pretty simple, but always keep in mind we could throw in any variations to these problems and find any way to add extra elements to make these problems a little more difficult. Well, thanks for watching.